Starting with sketching angles, particularly the focus will be understanding what an angle in standard position is. So one way of defining angles would be the rotation of a ray from a starting point called initial arm to the final position called terminal arm. So a ray would be just like a line. Usually we draw it like this with an arrow at the end. From a fixed point, a straight line with an arrow. And then we rotate it to a certain position. Let's say we stop there. And that would position where we stop, we draw the final or terminal arm. So now the angle is described by that rotation between the initial arm and final arm. And usually when we describe the angles like these using rotations, we use Greek letters like alpha, beta, theta, theta. And so far, we measured angles in degrees. If you think about triangles or any other geometric figures, these are all rotations, really, if you think about those sides being the arms of this angle. And if you give the vertices some names, A, B, C, I would describe angle A as BAC or CAB. Always put the middle of the letter as your angle, the letter in the middle as your angle. So angle BAC refers to angle A. But I can also call the angle A something else like theta or beta, whatever I want. I can call them or give them names. So the reason why we focused on the rotational type of an angle is because of the need of having a strict definition for an angle in standard position. So an angle in standard position would be an angle that has its initial arm on the positive side of the Cartesian plane. So right there, starting at the origin, and that's the ray straight on top of the positive side of the x-axis. And then the rotation can be either counterclockwise or clockwise. So if I rotate counterclockwise, we are describing a positive rotation, a positive opening or angle. So that'll be a positive angle. Positive angle in standard position. Now, if I draw another one, again, it has to start on the positive side of the x-axis, including the origin. But now I rotate it clockwise direction. That would be described as a negative angle. In standard position in this situation. So an angle can either be positive if rotation is counterclockwise, or negative if rotation is clockwise. Now we're gonna have a lot of situations where we have to refer to our angles and we have to add a little extra detail to their position. So the way we're gonna refer to the angles that have their terminal arm in either of the quadrants of the Cartesian plane is exactly by that quadrant. So an angle that has the terminal arm in quadrant 1, it's going to be referred to as an angle in quadrant 1 or quadrant 1 angle. It doesn't matter the direction of rotation. Either I rotate it this way or I go about clockwise and still end up in quadrant 1. They're both going to be angles in quadrant 1. So they're always going to be defined by their terminal arm, where it ends in which quadrant. So if it ends in quadrant 2, it's going to be an angle in quadrant 2. If it ends in quadrant 3, angle in quadrant 3, and so forth, right? Now, if the terminal arm is going to end up at 90 degrees, 180 degrees, 270, 360 for rotation, all of those ones are not really in either quadrant 1 or 2, either quadrant 2 or 3. They're always in between, right? So those ones are a bit special. They're called quadrantal angles. So all of the ones that end up on the axes are going to be quadrantal angles. Quadrants never change name. Just because you're rotating in an opposite direction than usually the normal one, which is counterclockwise for us, it doesn't mean the quadrants will change direction. So if I say I rotate here and I stop in this first quadrant in that direction, that's still going to be quadrant 4, okay? So 1, 2, 3, 4, always, no matter what, fixed. Now we're going to get into what's a radian, because if you did do trig in grade 11 pre-calc last year or a few years back, you did have a trigonometry unit circle and all that, and you did talk about a lot of these ideas there, but all of the angles you've seen, they were angles measured in degrees. What's a degree? It's 1 part of 360 of a full rotation of a circle, right? 1 out of 360. So a really tiny sliver of that circular rotation. We need a little bit of a different measurement for our angle, because it's more useful for the applications of trigonometry in other areas of mathematics and engineering and so forth. Because the relationship between the radian and the number line is a bit more closely related than 1 out of 360, which is the degree, okay? So to understand how or what we know about the definition of the radian is you need a little bit of recalling of the parts of a circle. So an arc of a circle is a piece of its circumference. So that's an arc. Let's put a center there. And then the central angle of a circle, it's formed by 2 radii. I'm going to choose 2 points on the circle exactly where I put my arc, just because, but so you see, and that would be a central angle right there. So that's a radius, this is another radius. So any 2 radii form a center, formed like, or meeting at the center, obviously will make a central angle. So now let's talk about what is a radian. I'm going to describe the radian using a standard position angle. So that means I start the rotation of 1 radian at the positive side of my x-axis, okay? So now, if you have a certain radius, in this case, my radius is about 3.5, so that's radius, 3.5 approximately, you measure it, and then you take that same distance and then you wrap it around the circumference of the circle, so about there, okay? That rotation of this arc with this radius right there, that's 1 radian. So the distance covered up onto the arc that's the same as the radius of that circle, describe 1 radian. So that would be 3.5 as well. So if the radius and this arc are the same, then you described 1 radian. So same length as the radius. So when the arc of a circle has the same distance or the same length as the radius, the measure of the central angle that we described, it equals 1 radian. Now, until you get comfortable thinking about the rotations in a circle using radians, you can quickly do a visualization of how big is 1 radian by using the conversion approximately 58 degrees. I would even go to 60 because you all know where 60 degrees is. So a little bit less than 60 would be 1 radian, okay? Just so you know, if you have to sketch about where to stop the rotation at 1 radian, 2 radians, and so forth, okay? The notation for radians is a little bit different than the one that we use for degrees. So if I want to say 1 radian, I would have to write 1 in the word radian. I can also use the shortcut of that. I could just say 1 rad or rads if you want plural. I can also say this angle is 1 or has the measurement 1. And if you don't put the word radians in there, it's assumed it's going to be in radians, okay? Now, if you're talking about degrees from now on, you always need to put the sign, the little like circle for degrees, because otherwise it's assumed to be radians. Make sense? Okay, so now let's do a bit more visualization now for radians and discover some of the important radians around the rotations in the Cartesian plane. So first of all, of course, we have radians as exact values, okay? So the first exact values would be the ones, you start with 1, 2, 3, and so forth radians. So that's gonna be our 0 radians when there's no rotation. So 0 radians. And again, if we take that length and we wrap it around, somewhere there would be 1 radian. This is really what I'm referring to when I say 1 radian, but I'm just going to put it up there around the circle, okay? So I don't crowd the inside of the circle. So 1 radian. So of eyeball it about there would be 2 radians. Just a little bit before 180 degrees, you will have your 3rd radian. And then in quadrant 3, somewhere there, you have your 4th. Quadrant 4, somewhere over there, you have your 5th. And just before a full 360 rotation, you'll have your 6 radians. So 1 full circular rotation would be 6 radians and a bit. Half of radian rotation would be 3 radians and a bit. We'll come back to this analogy in a bit, okay? Because we want to know exactly what that a bit is, okay? So if I go down here to approximations, I'm going to tell you now what that a little bit is, so we can go back to the previous circle and describe it exactly, okay? So this would be 0 radians, like we said, if there's no rotation. And like we said, it's about 1 there, about 2 there, about 3 there. When I have half a circle rotation, so the whole half of a circle, That's approximately 3.14 radians. That's right. So instead of writing 3.14, which is a decimal approximation of pi, we say we will describe half a circle rotation as pi radians. So that angle right there, half a circle rotation, that angle right there represents pi radians. That's right. That means 360 rotation, a full rotation would be now 2 pi radians. How about 90? Half of what? Half of pi, right? So 90 degrees now, exactly right there, it's going to be pi over 2 radians. That angle right there, half of it. How about here at 270? Well, so you have a quarter of a circle is pi over 2. How many? Not what I don't want the decimals. I want exact values. 4 over 3 pi. Okay. Well, a quarter is 1 pi over 2. 2 quarters is 2 pi over 2, which makes it pi, right? This is 2 pi over 2, right? Which makes it pi if you cancel the 2's. No, because it's only one extra pi over 2, another quarter of a circle. So 3 pi over 2. That's right. And then I go full rotation at the fourth quarter, you're going to get to 4 pi over 2, but that cancels to 2 pi, right? 45 is pi over 4. Yeah, we'll get down to. I just wanted to say that you can describe radians using exact values that involve the number pi, okay? But we will be more specific once we get to more exercises. But yeah, once you get to pi over 2 here, if you cut that in half, that's 45-degree angle. If you cut pi over 2 in half, in radians becomes pi over 4, right? So half of that right here at 45 degrees, you actually do pi over 2, which is 90 degrees, and you divide that in half, you get pi over 4 radians. So you can keep slicing up the pi into sections, and you get all of these fractional descriptions of radians involving pi. Pi over 3, pi over 4, pi over 2, and so forth. Yeah, you could, yeah. Yeah, you can count by pi over 2, you can count by pi over 3, you can count by pi over 4. Pretty much, yes, yeah.
What's pi r?
2 pi r? 2 pi r is the circumference length, and pi r squared is the area of the circle. 2 pi r squared would be 2 circles area. Yeah. Some reminiscence, huh? Of your darling years in high school. Yeah. Okay, so then let's go back now to decimals, because in some questions we do need to use decimals. So half a circle, 3.14. That means 90 degree will be half of that, so approximately 1.57. If I take pi and divide it by 2, I get approximately that. And of course, there's extra decimals, but we don't need them. And then for 270 degrees, or 3 pi over 2, that's approximately 4.71. And then a full rotation, double the 3.14, so approximately 6.28 radians, right? Now, if I ask you to sketch an angle that measures 2.5 radians, then you know in which quadrant that should end up with their terminal arm, right? And that's the reason why you need this representation in your notes. Any questions for page 6? Pi over 2, pi over 4, sorry. Pi over 2 divided by 2, which is pi over 4. Well,
But for the,
we will talk about families of angles a little later. So the ones that are related to pi over 4 would be the copy and paste of the image of this angle in each of the quadrants. So the reflection of that angle in each of the quadrants. So then you will have exactly a 45 that comes from here up there, okay? That's gonna be 1, 2, 3 pi over 4, okay? And then the one over here would be, again, 1, 2, 3, 4, 5 pi over 4.
and then 90s.
Yeah, but the 90 degree will not be part of the family of angles with pi over 4 because it's an angle that's different than that. Like it's not related the way we define the relationship between these families of angles. So we'll talk about them. So I love your enthusiasm, but we're not quite there yet. We'll be there soon. Soon enough. Okay, so right now we're just sketching. And Nick is looking up some important sketches for other angles beside the ones in example 1. 2 pi over 3. Yeah, ready? Okay, so now I'm going to teach you how to do the sketches using the pi. So you're looking at the slice of pi you're dividing into. So you're dividing pi into 3 equal parts, and then you're counting 2 of them, okay? So pi is half a circle. Now kind of eyeball it and divide it into 3 equal sections. The 3 equal sections are 1, 2, 3 over there. So the pi is half a circle. And each of those measurements for each of our sections are a pi over 3 radian measure. I want to sketch 2 pi over 3. That means if this is pi over 3, one of them, an extra one would be 2 pi over 3. Make sense? So now my angle is the one starting here and ending in quadrant 2. And this is the rotation direction because I wanted a positive 2 pi over 3. So it has to rotate counterclockwise. Yeah, which part? Yeah, I have 2 more there.
Yep.
3 more I have. There you go. Now I have stupid in the recording. Thank you very much.
I'm just not a fan of orange. Me and I gotta be.
Now I have to edit my recording and I don't do that. It's like just as they come. Okay. So negative 7 pi over 4 is the next one. So if we're going by the same approach, which is the very like sort of systematic approach, you can definitely do these ones a little faster later on. Is again looking at pi and the division of it into equal sections. So pi gets divided into 4 equal sections. Again, pi is half of your circle. You have to divide it into 4 equal sections. Okay, that means we're gonna have to cut one quadrant in half, another quadrant in half, like that. And because if I do so, I will have 1, 2, 3, 4 equal sections, but then I need to count 7. I will extend that into the other quadrants as well. Like that. So each of those sections described by this X right there to the origin describes a pi over 4 opening for the angle. Yeah, we will. Yeah, we haven't sketched it yet. We just described. Yeah, we just described the dimension that we call pi over 4. Okay. So now pi over 4 is again each of these sections like that, and we have to count 7 of them. And you're right, it has to be clockwise because it's a negative 7 pi over 4. So they all start with the positive side of the x-axis, and then we count 1, 2, 3, 4, 5, 6, 7. So it will be in quadrant 1.
Oh,
C, A, B, D, we'll skip C. That's your choice, right? Online, when you were on your phone, you were looking for C, right? That's right. Okay. So D, because we don't have a C, says negative 3 pi over 2. Pi over 2, we already know is 1 quadrant, right? But we have to go in the negative direction. So it's going to have to go 1, 2, 3 right there. Show direction, because you have to show the clockwise direction for negative angles. So now this one, it ends up on one of the axes. So this one, you cannot say it belongs in quadrant 1 or 2 because it's right in the middle. So this one is a quadrantal angle. Quadrantal. That's the word, quadrantal. It's on in your example 1 enunciation. It's right there, quadrantal. 25 pi over 7. These are the ones that are a bit more tedious because you have to divide the pi into 7 equal sections. One little clue that I can give you is when you divide by an odd number, you always skip the y-axis, right? So your divisions are like 3 in here. 1, 2, 3. And then the next one is right there. And then you have 7. So you have 1, 1, 2, 3, 4, 5, 6, 7. When you divide into like an even number, then your cuts are always gonna include your axes, the y-axis. So then once I do that, I just extend. You don't have to be accurate, so don't worry about accuracy at this point, because all we want is a sketch, not an actual drawing of that. We have a positive rotation, so counterclockwise 25. This is 0 radians. In terms of pi over 7, at pi, you would have 7 of these pi over 7 rotation, right? If I count 1, 2, 3, 4, 5, 6, 7 of them are pi, right? Does that make sense? But I don't have to go one by one. I just go in multiples of 7, right? So that's 7 pi over 7. At 2 pi will be how many pi over 7? Yeah, it is. Because I have to equal 2 pi, but I need that equivalent fraction that's divided by 7, 14. Okay, so a full rotation be 14 pi over 7. Now another half rotation is plus 7 more, that's 21. And I need to get to 25. So from 21 pi over 7, I just keep on counting. 22, 23, 24, 25. So right there. It's an angle in quadrant 4.
To like break it down and be like, okay, there's 7 to 25 3 times, we can go 3 revolutions, and then have the extra 4 versus after.
it doesn't work quite like that because the whole number you get, it doesn't equal the revolutions of your angle. Yeah.
So 7 half rotates, you're right.
Yeah, so you have to like break it down in terms of half circles or full circles, which are pi or 2 pi. And then it's, yeah, you just skip. That's what I kind of did. You skip the count until you get closer to the count you want, and then you go one by one. I won't give you a lot of these, but you need to kind of know the quadrants for some particular questions. So you need to know quickly how to sketch them. And once you get more comfortable, you're not going to need all the detail. Angles and radians, this time as decimals. So for these ones, you need your references to be those approximations for pi, 2 pi, pi over 2, and 3 pi over 2. So this is a positive 2 pi over 5, so 2.5 radians, so 0, 1.57, 3.14, and 4.71, and 6.28. So those are my references for each of those quadrantal angles. So then 2.5 would be somewhere in quadrant 2. Again, you don't have to be accurate, you just have to be sketching it. Because the important information is really here, the quadrant 2. And then the last one is a negative 3.9 radians. Same references, but make sure you write them in the opposite direction, right? So that would be 0 radians, but when I rotate this way, it'd be negative 1.57, and then negative 3.14, negative 4.71, okay? And we want negative 3.9, so again, quadrant 2, because 3.9 is between 3.14 and 4.7. Let's take a 5-minute break. Let's convert some radians from degrees to radians and vice versa. First, what kind of formula are we going to use for conversions? Well, a 180-degree angle, a half circle rotation would be the equivalent of pi radians. So if you make a ratio, either 180 over pi or pi over 180, that's sort of equaling to 1 because they're exactly the same amount, right? The same rotation. So you can use it as conversion. If you go from degrees to radians, then the degrees have to be at the bottom, so the units will cancel out. And then if you go from radians to degrees, you have to flip it upside down because now the radians units have to cancel out to become degrees, right? But it's basically the same ratio. You just have to flip it in the right order. So let's do example 2. We're going to do exact values, which we're going to be not using our calculator, so non-calculator for exact values, and then we're gonna use our calculator to get approximation for our degrees or radians. So 75 degrees, what is the exact value in radians? What we have to do is use this ratio, so times pi over 180 degrees. Degrees will cancel out. That's why we don't even write them anymore. And now, having no calculator, what we have to do, we have to simplify the 75 with 180. So what number divides both 75 and 180? 15. It might be 15.
I'm back to it now.
Sorry, is it 15? So 15 and 75, how many times?
Yeah, right. 15 to 60. 50 more.
That's right. So that would be what, 5, right? Because in 60 is 4, and then
Yeah.
one more, so 5 if we do 15. How about 180? 15 and 18 is 1, right? Once. And then 30, 15, that would be 2, right? Is it true? I guess so, right? 12 times,
And then 50 is 150 plus 30.
yeah,
30 divided by 2 is 50.
yeah. But that's, yeah, that's about right. So I'm gonna go with that. Do I have my key somewhere to double check? Yes, it's correct. So 5 pi, so 5 times pi divided by 12. 5 pi over 12 would be radians. If you want, you can put rad there. And that's the exact value. Good job. And now approximation, we just have to plug that into your calculator. So take your calculators out and then say 5 times pi, find the pi button, don't use 3.14. All scientific calculators have pi buttons on them. Divide by 12, and let's do 2 decimal spots for this approximation. One point, what? 308. So if you want 2 decimals or nearest 100, it'd be 1.31 radians approximately. Mm. 80 converted to radians times, again, pi over 180. They both divisible by? Did that after 15, you can give me something better, like you got 15. Now this one, you see it, divisible by 10, because they both end in 0, right? Yes. And now, or 20 is even better, that's right. So, but now we went by 10 because we cut the zeros, and now we can go by 2. So 4 and 9. So the final answer for the exact value in radians, 4 pi over 9 radians, which is approximately equal to so we're going to round to the nearest 100, we said, so approximately 1.40 radians. Right? Not always, but sometimes.
Just like, what do you got doing like Princeton
You just do 4 times pi divided by 9. And here, you just cancel, like, you just divide both numbers by a common factor, right? The first common factor we used was 10, so we divide both by 10. We simplify it, right? Yeah, it will get you the 1.396. So if you're not confident in your cancellation, then you just do that. Yeah. Yeah. I might, yeah. You have a calculator, so you can always find that common factor, right, using calculators. Okay, so 110 is our last one. You get the point of these, the way you have to cancel them. 110 or 180 is the one we do it. This one only cancels by 10, so we just get 11 pi over 18. Our exact value, plug that into your calculator, get it with 1.919. So 1.92, the nearest 100, 2 decimals. So no calculator, exact value, calculator, approximate value. That's exact. That's approximated. Yeah. The other way around, to convert from radians to degrees, again, the ratio between 180 and pi, this time pi is in the denominator. So let's convert 4 pi over 5 into degrees. We use 180 over pi. The beauty of these ones that are given to us already involving pi is that the pi will cancel out in the first go. And then we cancel out some of the numbers. 5 goes in 180 how many times? 5 and 18 goes 3 times. We have a leftover of 3, 30. 30 divided by 5 is 6, so 36. Long division, mental math. That's it. It's like 5 goes in 18 how many times? Or 18 divided by 5 is what? 3, right? And then you have a leftover of 3 from the 15, right? And then 30 with a 0 divided by 5 is 6. So you get the answer. And then 4 times 36 is, 4 times 30 is 120. 4 times 6 is 24. So 144. Degrees, don't forget the degree sign, because if you forget it, then you're saying it's radian, okay? Converts 2.35 radius to degrees. This one you need a calculator, because you, the only thing you can do then is just multiply them and that's it. So with your calculator, multiply 2.35 with 180 and divide by pi. Again, use the pi button. We get an approximation of 134.6 degrees. So these should be pretty straightforward, right? When in doubt, you always have your conversions to kind of visualize, but don't always rely on conversions, because some of the radians have to be used as radians. 1.2, we'll skip it for now. Let's do some radians in word problems. And all of our word problems in one way or another would use the formula for arc length. So to get to the formula for the arc length, let's imagine a wheel in motion. When the wheel is turning, the points on the circle that touch the ground will describe a certain linear distance that would be related to how big the circle is, right? And how big the circle is, it's related to how big the radius of the circle is, right? And the linear distance would be that circumference of the circle that now kind of unraveled as a linear distance. So now the formula that will show us this distance that's described by the rotation of the circle will be dependent on the length of the circumference, and the length of the circumference is usually described by the rotations or the angle in the center of this circle. So this S stands for the arc length, and then the theta is this angle in radians, the central angle in radians, and then times the radius will give us the linear distance of that circumference coverage. Now, one thing we have to be careful is that this theta is always going to be in radians. So if the question tells you something of a angle inside the circle that's in degrees, before you plug it into the arc length formula, you have to convert it into radians. Okay, so let's do the visual. If it's not a full rotation, it will always be That's S, that's theta, and that's radius. So S is a piece of the circumference if the rotation is not a full circular rotation, and then it goes beyond if it's more rotations than one. It's like a coil that kind of unravels. Okay, example. If a tire has a radius of 0.5 meters and it turns 75, attention to degrees, 75 degrees, we have to convert it. How far did it travel? How far, or a question about distance, would be always arc length. So 75 degrees times pi over 180. I feel like we've done this conversion today. Am I remembering? Is it 5 pi over 12? Yeah. This is the one you said 15, right? So that's 5 pi over 12 radians. We need how far did it travel? So we have to use the S equals theta R. Theta is 5 pi over 12 because we always need it into radians. And the radius is 0.5. If you want, you can convert it in 1/2, so it's a little easier to work with. Like that. So you get 5 pi over 12. The arc length always matches the radius length in terms of units of measurement. So if I'm measuring my radius in meters, my arc length calculation will also be in meters. Make sense? If they're not the same, then you have to make them the same before you plug them into your question. Okay? So 5 pi over 12 over 24, because it's times 2. That's what you wanted to say, right? So 5 pi over 24 is the length of that rotation. But this is a hard number to imagine. What does that mean? 5 pi over 24 meters. I don't understand it. But if the question says, give your answer in terms of pi as an exact value, this is your final answer, right? But for picturing a little bit of a better distance, plug that into your calculator and we get approximately 0.654 meters. So again, this is an exact value in terms of pi. That means we leave pi in the answer. And that's going to be the approximated answer, which again, it's a little bit easier to picture with 0.6 of a meter. Find the central angle in degrees of a circle with a radius of 2 centimeters and an arc length of 7. So we have radius of 2 centimeters. We have arc length of 7 centimeters. We're asked for theta, but we want to make sure that we convert it in degrees in the last step. But between the givens and what I'm looking for, the R, S, and theta, we only have one formula, right? So it's S equals theta R. Plug in, S is 7. Theta is what I'm looking for, and R is 2 times 2. Theta is equal to what? 7 divided by 2, or 3.5 radians. This is not the final answer because they want our central angle in degrees. So last step you have to do conversion. So 3.5 radians times, now you want the ratio 180 and pi. Which one goes at the top and which one goes at the bottom? At the top, right? So 3.5 times 180 divided by pi, we get approximately 200.53, so approximately 200.5 degrees. Yeah, that's one of the symbols we use for approximation. Sometimes we use that, sometimes we use that. It just means it's not perfectly equal. Good. Any other questions? It's just approximation. It's the same, like different notation for approximation. 1.3. Another break, 5 minutes. 8:30. Coterminal angles, the next type of angle that you have to learn the definition for. Two angles that share the same terminal side or terminal arms are called coterminal. So 45 degrees angle, that one over there. And this negative 315 angle that again shares or ends in the same spot. Those are what we call coterminal angles. I sometimes tend to leave the initial arm out because all of the angles we draw are in standard position. So I just focus on the terminal arm. But if I forget, remember there's an extra arm there on the positive side of the x-axis. Well, how many other coterminal angles we can create for the 45-degree angle? So one I already did to show the definition, the negative 315. But what if I do a positive one that goes one full 360 rotation and then an extra 45? So the 405. That's another one. Can you think about another one? Hmm? An infinite? Yeah, an infinite, because I can keep adding rotations and still stop at the 45 in quadrant 1, right? And in both directions. So there will be an infinity of angles that are coterminal to a given angle in standard position. Make sense? Just all extra rotations of 360 in both directions. So to show that relationship, that idea of an infinity possibilities for our coterminal angles, we can write them using this formula. So think of theta being your 45-degree angle. And to create all of the possibilities of coterminal angles with 45, you just add multiples of 360. So K stands for how many 360s do you want to add? 0, it will give you 45 degrees. 1, it will give you this angle in blue that I just showed you, right? -1, that means it will give me the negative 315, right? Because I'm subtracting 360 from 45, right? So the 1 is, when we say an integer, or -1 is an integer. So to show that, we say K belongs to Z. K belongs to the set of integers. So Z are integers, like these. And I'm putting these ellipses here to show infinity, right? To show that it goes in that direction, infinity, to infinity. And then if I talk about angles and radians, then I have to replace the 360, the one full rotation, with 2 pi, because that's one full rotation in radians. So the same formula will apply to get any coterminal angle. It's going to be theta, the given angle, plus 2 pi k. K stands for how many rotations you want to add or subtract. So k will be an integer. Make sense? So let's practice with these two formulas. Find one negative and one positive coterminal angle for each of the given angles below. So this is the given angle. So in the formula, that's going to be your theta. So when I say one positive and one negative, it doesn't mean it has to be my positive angle, right? And my negative angle. These answers may be different depending on what kind of value of K you're choosing, right? Usually the ones that I'm looking for are the smallest ones. I don't need to really calculate with large numbers, okay? So let's go for the positive one first. So that means 430 degrees and then plus, and I'll use the 360 formula because my angle is in degrees, right? Plus 360 degrees. And you can go positive one for your K here, or you can go negative one, because even when you subtract 360 from 430, you're still gonna get a positive angle. Does that make sense? Okay, so I can do negative one there. And we get, see which answer do I have for these ones. I did this one in my notes too. So we get 70 degrees, so positive 70. And then for the negative one, 430 degrees plus 360. And then I do that twice, right? Or you can, if you don't want to do this negative or positive, just subtract 360 twice, right? Or 720. Which is negative 290 degrees. That's my positive one, and that's my negative one, but again, it doesn't have to be that. You can choose -3 there and get a different one. You still found a negative angle that's coterminal to 430. And you can choose here 3, right? +3 and get a really large angle. That's again still coterminal angle with 430. Here? Okay, nice. One more. Negative 540, another one that's in degrees. So let's do the positive one. Negative 540 is again our theta, the given angle for the formula. And then we add 360. Now we have to choose the K, the rotation in such form or in such multiple, so it covers the negative 540 and more, right? Because we're going to get into positive. So one's not going to be enough. 2 is 720. 2 is going to be plenty, right? But you can choose 3, 4, 5, doesn't matter. As long as it's at least 2. And that's 180 degrees. And for the negative one, again, here, I don't have to choose necessarily a negative K to give me a negative angle. Because here, if I just choose one rotation to add to 360, I'm going to get negative 180. The goal is to get either a positive or a negative angle. It doesn't really care what K is. So the sign of K doesn't have to match the sign of your final answer. Let's do some questions now with radians. It's the same type. So what is some positive and negative coterminal angle with negative 5 pi over 4? So negative, let's do the positive one first. Negative 5 pi over 4. We have to add 2 pi multiples. So I want to do 1 just to begin with, but if you want to be certain, you can definitely go higher. Now, in order to add fractions, you have to write 2 pi as a fraction over 4. So you have to create that equivalent fraction, right? So that would be 8 pi over 4. That's equivalent to 2 pi. Make sense? Okay, now we keep the 4 and negative 5 plus 8 is 3 pi over 4. That's our positive angle. Yeah. The negative. We're going to subtract 2 pi rotation. So 5 pi over 4, negative 5 pi over 4 minus 8 pi over 4. So that equivalent fraction again in terms of pi over 4. And we get negative 13 pi over 4. Depending on the angle you're given. If it's a large angle, you might have to subtract multiples, right? If it's a large negative, you can just probably stay in the negatives, right? You can still subtract if you want. Like this, the sign doesn't have to match whatever your goal is. It's like in the previous question. Right? That's right. You have to add or subtract multiples of 360 or 2 pi, depending on the measurement, if it's in radian or degrees. That's going to give you always the ending in the same location. You can't add just 20 degrees. You have to always add multiples of 360. Because if you're here, let's say your angle is here, that's 45, and then I add 20 to it, like right, I get another angle. It's not a coterminal angle. So what we do is find angles that end in the same spot with this, right, the terminal arm. And that only happens if you add or subtract a full rotation, right? Because you basically just switch the or add the extra rotations to it. 145 is a radian angle, so the same formula will apply. So 1.45 plus 2 pi times 1. This one you need a calculator for to get an approximation for it. So approximately 7.73. And the negative one, 1.45 plus 2 pi, negative 1. You can go straight to subtract 2 pi if you want. 1, subtract 4 pi, subtract 6 pi, as long as it's multiples of 2 pi. Which is negative 4.83. And negative is just a shortcut that I'm writing negative. So I'm replacing negative with the negative sign, and I'm writing VE. Just means negative, yeah. Write a general expression for all angles in standard position that are coterminal with each of these ones. So for a question like this, all you have to do is write the formula, but for this particular angle. So if theta is 30, you replace 30 degrees for theta in the formula, and then plus 360 times k, where k belongs to z, because this particular expression written like this accounts for all coterminal angles for the angle 30 degrees. Right? Because all I have to do is now change k, and I found them one by one. How many possibilities are there for coterminal angles? Infinite. And the other one, 4 pi over 5, you have to just, again, be careful with the measurement. It's in radians, so it's 4 pi over 5 plus, you have to use 2 pi k for this one. K belongs to z. reference angles. Okay, so now we're getting to that first question that you were wondering about. How about 45 degrees in quadrant 2, right? A family of angles idea. So reference angles are kind of like the family name of a family of angles. So let's first give a definition. For every angle in standard position, we can describe an acute angle between 0 and 90 degrees, or between 0 and pi over 2 radians, if we're talking about angles in radians, that is found between the terminal arm and the x-axis. This is what we call a reference angle. Angles that have the same reference angles in terms of the measurement, they are related, and we say they belong to the same family of angles. I'm going to give you a series of formulas in the first rotation angles. So positive angles between 0 and 360, or between 0 radians to 2 pi radians, okay? But you can adapt these formulas for whatever other types of angles because of the way the reflections are working in those 4 quadrants. You'll see right away. You don't need to stick with these formulas. That's just for your support. But once you understand it, you can just use them only when you need them. One important note, though, for quadrantal angles, we have no reference angles. Where's the G? Angles, yeah. Ankle. How would you say that if that's a Q? Ankles? No, that's how you spell ankles, all right?
Still sound.
Sounds the same. Okay. So reference angle. So let's say we have this angle in quadrant 1. That's the angle theta in quadrant 1. By the definition of reference angles, what you have to do is find the shortest way from the terminal arm to the x-axis, and that's going to be your reference angle. It doesn't have direction reference angles, it just has quantity, how big that angle is, okay? So this is the terminal arm. If I go straight down to the x-axis, that is my reference angle. So for any angle in quadrant 1, reference angles and the angles themselves have exactly the same measurement, okay? They're the same thing. So that is the formula here. Theta r, the reference angle of the angle theta, is the same as the angle itself, angle theta. I like to show reference angles using double lines like that. Okay, and the actual angle has a direction like that. So the red one is my reference angle, the blue one is my actual angle. Okay. Now let's say now we have an angle in quadrant 2. This one right there. That's our theta. To find the reference angle for angle theta, again, you go for the terminal arm and then find the shortest distance to the x-axis. Okay, so that right there is our reference angle for this particular angle. And if I have to connect it to other members of its family, all you gotta do is reflect it in the first quadrant, because usually those are the angles we're gonna memorize, the first quadrant angles from the family of angles. So this one would be related to that one that has exactly the same reference angle in quadrant 1. So you take that and you just reflect it in quadrant 1. You take that one in quadrant 3 and 4 reflection, and then you have all of the family of angles in all of the quadrants. So that the reference angle, again, theta r. How do you find it? Well, you're going to use relationship with 180 degrees because that's where we went. We went to the line representing 180 degrees, right? So if I take 180 degrees and take away theta, I'm going to get the value or the measurement of theta r, how big it is. And that is the formula We're finding theta R for angles in quadrant 2, positive angles in quadrant 2. Okay. If you want to use pi, it'll be pi minus theta. But you have to use pi. Now in quadrant 3, angles look like this one. This is an example of an angle in quadrant 3, positive rotation. Reference angle, again, you take the terminal arm and find the shortest distance to the x-axis. That's your theta r. How do you find that section? Again, in relationship to the 180 degrees. Now, our full rotation for quadrant 3 angle goes beyond 180. So if I take away the 180, I get that section, right? So the angle itself minus 180 is how you find theta r. The formulas are not, you don't need to memorize them. You just look at the diagram and you understand what the theta r is, the reference angles, and you just create the formula yourself. How do I get that angle in red if I know the angle in blue? Okay. Quadrant 4 would be this angle right there. That's the reference angle for an angle in quadrant 4. How do I find it? Well, if I take 360, one full rotation, and take out our given angle, the theta angles, which are the blue ones, you're going to get that little section right there, which is theta r. So 360 minus theta, or 2 pi minus theta, it's going to give you theta r. So all of these formulas, if you need radians, just replace 180 with pi, or replace the 2 pi or the 360 with 2 pi. The same thing. Okay, like I said, I'm not a really big fan of the formulas because the diagrams always are more helpful. You just need, again, to have a really good understanding what the reference angle is when you look at the diagram. So let's do example 6, and I'll show you how I approach these questions usually. 150 degrees is the given angle, and you have to find the reference angle for these given angles. The first thing what I do is I sketch the angle. It doesn't have to be, again, accurate sketch, just approximately, but make sure you get the accurate representation of where is the quadrant of that angle, right? So 150 is between 90 and 180, right? So I make sure that it's in quadrant 2, my representation. That's my angle 150. And I need to find theta r for it. So again, shortest distance from the terminal arm to the x-axis, that will be my theta r. Okay, yeah, it is 30. So that's what I'm saying. You don't need to memorize the formula. It's like, okay, how can I get that section? Because I know half the circle is 180. I know this section is 150. If I subtract them, I get the other part, right? So the formula is for theta r, 180 minus 150. So theta r is 30 degrees. And again, theta r, or reference angles, don't have signs, don't have direction. That's why I always like to write them with 2 lines. I don't use arrows for them. It's just how big it is. $715. Now, when we have angles that are more than one full rotation, what we could do is just take away the rotations until we get to an angle in the full first rotation, because they are coterminal. They will have exactly the same reference angle. So 715 minus 360, how many times will get me in the first rotation? Once, right? And I'm getting to what? What's this 360? take away, how much?
For, yeah, 355.
355, yeah. That's what I was saying. I thought you said that you have to leave two, because now you're getting over both. Okay, okay, yeah, 355 is correct. So now that I have 355, it's a little bit easier to work with. I don't have to add all those extra rotations when I sketch the 355. It's an angle in quadrant 4. And theta R is that one. Which is how much? You already said what it is. Twenty pi over 6. Now, the first thing that I would always recommend is if you have a given radian angle in a fraction form, always simplify if it's not in simplified form, because if you don't, you might get into the trap of thinking that pi over 6 is your reference angle, okay? So if you can simplify the fraction, you're gonna get an equivalent fraction. It's the same angle, okay? Don't be scared of it. Now, 20 and 6 cancel by 2, so we get 10 pi over 3. Now, is 10 pi over 3 in the first rotation, or is it extra rotations? Extra rotation, because 2 pi is equivalent to what? In pi over 3 sections. As a fraction over 3. 2 pi equals to what? 6 pi over 3 equals to 2 pi, right? So that means if I want to get this angle into the first rotation, I have to take away 2 pi, right? So plus, if you want 2 pi minus 1, we're doing those coterminal angle situations here. So then be 10 pi over 3 minus 6 pi over 3. So 4 pi over 3 is the angle I'm trying to find a reference angle for. So question B and C are the same type of question, but one was in degree and this one is in radians. Okay, you just have to bring it to some representation in the first rotation. Four pi over 3. Remember the way we sectioned off our pi into 3 equal sections like that. And then we have 1, 2, 3. The 3 pi over 3 is right there at pi, right? And that means I need an extra 1 to get to 4 pi over 3. Make sense? So it's an angle in quadrant 3. 1, 2, 3, 4. That's my angle. Now the actual angle, the 20 pi over 6 or 10 pi over 3 will have an extra rotation like that, but we removed that and we got a coterminal angle with it. So 4 pi over 3, we need the theta r for 4 pi over 3. We're in quadrant 3. Theta r is that section. You can do the math for it, but you can also see how much it is, how big it is. Well, if each of these sections we counted was pi over 3, 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, what's the one section? Pi over 3, that's right. But the math behind it is 4 pi over 3, the given angle, minus half a circle, which is pi, right? Or 4 pi over 3 minus 3 pi over 3, which is pi over 3. But you can clearly see it's just 1 pi over 3. That's theta R. That's Q, quadrant, not theta, quadrant 3. Okay. Now working with a negative angle. Let's sketch that one. Negative 105. Well, you have to, again, make sure you have the right rotation. And negative 90 is here. So you want to go a little bit extra in that direction, in the clockwise direction. Theta R will be from the terminal arm to the x-axis all the time. Always like that, always towards the x-axis. So it doesn't matter, like, if this is the quadrants, right? It doesn't matter where your angle is, okay? You always go down to the x-axis with the quadrant 1 and 2, and up to the x-axis with quadrant 3 and 4. So you're always like in between here, like making angles with the x-axis. Those are your theta R's all the time. Clear? Okay, that's just extra. We need that one particularly. So how do we find that one? Because this is 105, it's just negative, but that's direction, right? So you don't have to be to stick to the formula per se, because now you have negative angles, and the formula that I gave you only work for the positive angles, right? So you can just think this rotation here is 180, right? So 180 minus 105, we get 75. So you can create your own formulas just to get to the sections that are theta R. No, because theta R's don't have direction, okay? Your angles have direction, but not the reference angle. So it would be 180 minus 105, which is 75 degrees. That's theta R. If you want to use the formulas, you have to find the positive coterminal arc with the coterminal angle with 105, and then use that one with the formulas, right? It's just a little extra work that you don't really have to do. If you understand, again, the formulas or the definitions of the reference angle. And the last one, the negative 2.76. To sketch that one, you need to know your angles as decimals. So if you forget them, you just go to pi. So negative 3.14 is there, and then you do in your calculator 3.14 divided by 2. So you get the 1.57 right there. And then for here, you just add 1.57 to 3.14, or take the 1.57 and times it by 3, right? And you get to 4.71. And this is double that, so 6.28. We're doing all negative directions. That's why we're putting all negatives, right? So I need negative 2.76. So somewhere there in quadrant 3, theta R. Again, we can use just our brains to figure out, how do I find that section? If this angle is 2.76, just in the negative direction, we can ignore the negative. Just remember that half rotation is 3.14 or pi. It's the same thing like this one, right? So pi minus 2.76, we get, yeah, I got it. It's 0.38. It's missing here on the line is just 0 radians to 2 pi radians. Zero and 2 pi, it's just the equivalent of 0 degrees and 260 degrees. 0 and 2 pi radians. find two angles that have the same reference angle as 220. So this question has some steps to it because one, you're given an angle and you want to find other angles in its same family, but you don't know the family name, which is the reference angle. So your first step would be find the reference angles. And once you have that, you can find other angles, okay? So two angles is what we want that have the same reference angle. So this is step one, find the reference angle. And step two, then you can do the other angles you're looking for, okay? So step one, we've done already in example 6. So let's do a sketch for 220. 220 is between 180 and 270. So quadrant 3, make it in green. And then we want the reference angle right there. Can tell me how to find the reference angle for 220. How did you get to 40? Subtract it. Yeah, what do we subtract? Okay, and we get 40 degrees. Okay. So now once you get the 40 degrees, all you got to do is take this section and reflect it in whatever quadrant you want to find those other angles. The way I do it is using my ruler and just do extension of that terminal arm. In this situation, because it's in quadrant 3, it's going to extend in quadrant 1, like that, right there. And then I do like the reflection of that whole line, approximately, of course, in the other 2 quadrants. And then around the interior of this X that I created, all of those reference angles live, right? And then if I want to find other family members of this family of angles, all you gotta do is find those angles that end up there on those X's, okay? So for example, if I wanna find an angle in quadrant 2, what I need this angle right there. How do I find it? When I know this section is 40. That section is 40. What's going to be this angle in quadrant 2? $180, take away 40, right? Yeah. So this is one family member that has the same reference angle with the 220. They both have 40 degrees as their reference angle. They share the reference angle. Now, if I want to find another angle in quadrant 4, okay, that means I have to do or bring my focus to this terminal arm of my X that I created right there. And I have to find that angle. It doesn't say find the positive angle, so I could find either this one or that one that has the same reference angle. So how do you find it, Antonio? You just nodded, so you know it. So if this is the angle that I want from here all the way there, and this is the reference angle, that section, how do I find the blue angle? Because the full rotation is 360. And that's 40. This section is 40. What's going to be the blue? That's right. See? You got it. I could have picked the quadrant 1 too, but that was just too. Right? What was the angle in quadrant 1? 40 degrees. Because reference angles and the angles in the family, they're always going to have the same value in quadrant 1. It'll be the same thing. Okay, let's do one with radians. Negative 3 pi over 4. So the step number 1 is to find the reference angle for negative 3 pi over 4. 3 pi over 4 means these are my sections right there, the negative direction clockwise. 1, 2, 3, right there. They're all in quadrant 3. Right? And now the reference angle is that piece right there. And that piece right there, and that piece right there, and that piece right there. But what is the piece that I'm looking for? 2. That's random. No. It's the section which represents what angle? Because we counted as multiples of pi over 4. Pi over 4, that's right. So our reference angle is pi over 4. Because this is 3 pi over 4, and an extra one is 4 pi over 4, which equals to pi, right? So, right, 1, 2, 3, 4, pi over 4 equals to pi, right? So 1 less 3 pi over 4, an extra one, an extra pi over 4. So that's our reference angle. Now let's find those 2 extra ones. You choose the quadrant now. Quadrant 1. He wants the one in quadrant 1. That's right.
No way.
Yes.
That's crazy.
My God, you guys are awesome. I'm so excited. You're getting it. So that's the angle, right? The angle in quadrant 1 is the same as the reference angle. So it's pi over 4. Now another one, either quadrant 2 or 4. It's the quadrant 4. That's right. If we want to choose a negative angle in this direction, I stop there, is negative pi over 4. The same reference angle. If I do positive direction, would be what? That's right. Yeah. In quadrant 2, what do you think it's in quadrant 2? 1, 2, 3 pi over 4. And the negative one in quadrant 2 would be? Not the same thing, no. 1, 2, 3, 4, 5 pi over 4. Negative 5 pi over 4. That's right. Yeah. It's all the counts. That's all it is. Just counting. So there's our 2 angles we found. One in quadrant 1, one in quadrant 4. But look at us. We finished the whole thing. One more example. For each given reference angle, find the family of angles in the interval stated. Sketch a diagram. So for the angle 30 degrees, find the family of angles between 0 and 360. This is 30 degrees. Yeah, pretty much. Yeah. So from 30, I'm doing the reflections because again, in quadrant 1 is the same reference angle. That's right. All of these ones are the 30 degree, right? The reference angles right there inside that X. But what you want is you want the angles that end on these lines that make the X. So in quadrant 1, it's going to be the same as your reference angle. It's 30 degrees. It's this angle right there, right? In quadrant 2, it's going to be this angle right there, which you said it was 150, because I have to do 180 minus 30. So 180 minus 30, which is 150. In quadrant 3, will be that angle right there. So I have to do 180 plus 30, which is, that's right. And in quadrant 4, gotta do that angle, which is 360 minus 30. Which is 330. So these are all the family of angles with the reference angle 30 degrees. This is a given theta r reference angle. Pi over 4, but in the negative direction, yes. So pi over 4 would be like that, right to the middle. So every single one of these sections will be pi over 4. That's theta r. So what we want this angle in quadrant 4, this angle in quadrant 3, this angle in quadrant 2, and this angle in quadrant 1. And what I like to do is start from quadrant 1, because quadrant 4, because it's easier. So quadrant 4, the negative angle is how many pi over 4? Negative 1 pi over 4, because it's just one of those sections. And then in quadrant 3, you have to go 1, 2, 3, so negative 3 pi over 4. In quadrant 2, how many pi over 4s? 5 pi over 4 negative direction. And in quadrant 1, 7, because the full rotation will be 8 pi over 4, 1 less, 7 pi over 4. These just need a bit of practice, but once you get it, it's just done, you know? You don't have to worry about it anymore. And pi over 3 in both directions, positive and negative. And when we finish that, we're done. I want to do 2 rotations for this one because I want to be more. Pi over 3 is 60 degrees, so it'll be like a steeper like that. X. And it skips the y-axis, the count. So it's 1, 2, 3, 4, 5, 6 in total. The theta r, the pi over 3 are right there in the center. Okay, so let's do the positive direction. This one here would be pi over 3. In quadrant 2, 2 pi over 3. In quadrant 3, 4 pi over 3. And in quadrant 4, 5 pi over 3. And the negative direction, start with quadrant 4, exactly the same thing, but backwards, right? So negative pi over 3. And then negative 2 pi over 3 for quadrant 3. This guy here is negative 4 pi over 3 in quadrant 2. And the one in quadrant 1 is negative 5 pi over 3.
So what about the quadrantal angles, the ones that land on the x-axis?
Those ones are not the same family of angles because they cancel out to pi or 2 pi, right? And remember, quadrantal angles don't have reference angles, right? Yeah, that's fine. Yeah, perfect. Yeah, great question. Okay, so the family of angles are always, again, living around those x's, okay? So the way we find them is using those angles that create those x's, and then we just have to count what catches the terminal arms that form those x's. Make sense? So it's only the ones that we see with the reds here. So we skip the other ones, even though we count them to help us find the actual angles, so they're not part of the family of angles. Okay. Good job, everyone.